integral is two main things, an antiderivative and the area underneath the curve. Well, this is climb time, and in this video, we're going to specifically look at the integral as an antiderivative. All right, I have a definition here, and that is capital F, if I take its derivative, will give me little f. So the derivative of the function capital F of x is little f of x. What that means is that capital F now becomes the antiderivative. So what we could say is the antiderivative of little f is capital F, right? So this is derivative. So the derivative of capital F is little f. That means the antiderivative of little f is capital F. So that's how we're going to define things. That's pretty typical in how things are defined. So whenever we learn an operation, like in different parts of our mathematical career, we learn addition first. After we learn about numbers and counting, we learn about addition. We learn about how to go backwards. So if we learn how to add, we learn how to undo it through subtraction. We learn how to multiply, we learn how to undo it through division. And as you go along the range, you start learning about more complex things like exponential functions and how to undo them with logarithms, or vice versa. Maybe they start with logarithms and undo it with exponential. So there's always an inverse function for every function we learn. And once we learn derivatives, then the next step is to learn how to take an antiderivative. So if I can take a derivative of a function, that means I should be able to go back to the original function through an antiderivative. So let me give you an example here. So I have an example that capital F of x is equal to x squared plus 1. So therefore, if I take its derivative, f prime of x, it's going to equal the derivative of x squared is 2x, and the derivative of 1 is 0, so that goes away. So that means little f of x, which is equal to f prime of x, is going to equal 2x. So little f of x is the derivative of capital of x. But that means the antiderivative of little f of x is going to be capital F. So if I want to take the antiderivative of f of x, I would get, I forgot the x. I don't know how that happened, 2x. Okay, so how do I get from little f to capital F? How do I do an antiderivative? Well, the answer is that you just do everything backwards. So how did we get from x squared to 2x? Well, we took the 2 and we moved it to the front and we multiplied it by the coefficient that was there. The coefficient that was there is 1, so 2 times 1 is 2. And then we subtracted 1 from the power. So instead of 2, we now have 1. So you move the coefficient, you move the power to the front, multiply by the coefficient, subtract 1 from the power. That's how the power rule works for derivatives. So if I want to go backwards, back to capital F, I'm going to have to go backwards. So what we're going to do is we're going to add 1 to the power. So we go from 1 to 2. And then instead of multiplying, we're going to divide by the new power. So you add 1 to the power. So that's why it goes from 1 to 2. And you divide by the new power. So you divide by 2. And 2 divided by 2 is 1. So we're going to be adding to the power and dividing by the new power, as opposed to multiplying by the power and then subtracting 1 from the power. So you just do everything backwards. Now the question is, where does the plus 1 come from? Well, that makes things a little bit interesting because it turns out that there are many possible antiderivatives. This is one possible antiderivative. Another possible antiderivative could be x squared plus 2. Another possible antiderivative could be x squared plus 3 or x squared plus 4. So it could be any constant over here because when we take the derivative, the constant goes away. So that's kind of the way it works when you have constants and derivatives. So when you go backwards, there's an asymmetry here. When we're going forwards with the derivative, we're going to get one specific answer. But when we go backwards, when we take the antiderivative, there is a family of answers. We'll look at that in a little bit. But all the answers will have something in common, and that is that all have to be plus some constant. So we'll take a look at that in a little bit. But anyhow, f is the derivative. Little f is derivative of capital F, and capital F is the antiderivative of little f. All right, so let's take a look at the process here. And so we're going to go through, and I'm going to go ahead and do this in green. So let's say we have f prime of x equals little f. So another way of saying that would be like df over dx is equal to f of x. Another way of saying f prime of x. Okay, so it's just another way of writing the same definition. Now what I can do is I can multiply both sides by dx, and what I get on the left is d capital F. What I get on the right is f of x dx. And what that means is have a little tiny piece of the capital F function. A little tiny piece of the capital F function is going to be a y value times a little tiny piece of x. Now what I can do is I can integrate both sides. So I can take the integral of df on the left and the integral of f of x dx on the right. And I can take it from some a to some b to x values like such. And what that does is, what we know over here, we know that that part right there is going to be the area underneath the curve. We know that that's how that works. That's the area under the curve. We learned about that in other videos. Okay, and that's true. It's the area underneath the curve. And what we have on the left is we have a little tiny change in capital F. But what this integral represents, it represents the sum of all those little tiny changes. So if you have a sum of all those little tiny changes, what you end up with is the overall change in capital F. So we end up with the overall change in capital F because it's the sum of all the little tiny changes in F. And so once we do that, the definition of a change in capital F means it's capital F evaluated at B minus capital F evaluated at A, and that is the definition of change in F. But this is also equal to the integral of f of x dx from A to B. So while this is area underneath the curve of little f, that's true, it's also equal to a change in capital F, which is the antiderivative. So what I want to point out is this, is that when you take the integral of a function, we can find the area underneath the curve from A to B. That's one thing we can do. But another thing you can do is you can find the antiderivative because capital F is the antiderivative. So to get from here to here is an antiderivative. So I'll put that in antiderivative. So there's two ways to evaluate this. One way to evaluate is to find the area underneath the curve. The second way to evaluate this is to take the antiderivative, plug in B, plug in A, subtract one from the other, and you get the same value. So you get the same value, but you find the area underneath the curve, or if you take the antiderivative. So either way works. Okay, so if you have something called a indefinite, this is called a definite integral. You have something called a definite, this is called a definite integral. You have something called an indefinite integral, indefinite. So that means basically you have no bounds. So an indefinite integral will look like this. We have an integral of f of x dx, and notice there are no bounds on it, nothing here and here. We would find the antiderivative. So this would be capital F of x. Because we can't find the area underneath the curve because there's no bounds. If there's no bounds, we can't find the area underneath the curve. So this is like a similar notation to our notation we're used to. It's just that the area underneath the curve is not possible now because there are no bounds on it. So basically, this is just a notation to say find the antiderivative. However, as I pointed out with this example up here, the antiderivative, there's not just one antiderivative. There are a bunch of antiderivatives. In fact, we'd say it's a family of antiderivatives. But what they all have in common is they are all going to have a plus c. And the reason why is because when you go to take the derivative of this, the derivative of capital F of x is going to be little f of x, but the derivative of c is 0. So if I took the derivative of this side on the right, I would get little f, which takes us back to our definition right there. So the derivative of capital F, the derivative of the entire right side, is going to equal little f of x. So this is an indefinite integral. The only way you can do this is through an antiderivative. So I'll write that down. Antiderivative is the only possible solution here because we have no bounds. And so we can't find the area if there are no bounds. So antiderivative, and what you're looking for is an equation or a function? The answer is a function. So it's an antiderivative is what you're taking, and what you're going to get when you're done is a function. But when you're doing it this way, you can find the area underneath the curve if you want, and you can find that area underneath the curve through geometric formulas. You can find the area underneath the curve by doing a Riemann sum and approximating values, taking enough rectangles to be close enough. So underneath the curve is perfectly appropriate here. Or a second way you can evaluate this is that you can take the antiderivative and plug in b and plug in a and subtract one from the other. So there are two ways to solve this type of problem. And this is called the definite integral. So I'm going to identify that now. So definite integral. And if you have definite integral, that means you have bounds. And you have two ways to solve it. You can solve it through an antiderivative, or you can solve it by finding the area underneath the curve. All right. But what you're looking for when you're done is you're looking for a number, basically. Not always, but typically you're looking for a number. Okay, so if you do it this way, you're looking for a number. Your answer will be a number, and you can find that number, again, by finding the area underneath the curve, or by taking the antiderivative and subtracting your two endpoints, your two bounds, your b and your a, and that's for a definite integral. And for an indefinite integral, you find the antiderivative, and what you're looking for, your answer will always be a function. Now, real quick, not every function has an antiderivative. So while every function has a derivative, so every capital F function will have a derivative, little f, but not every little f function will have an antiderivative, capital F. So antiderivatives are tricky. There's a whole long list of processes to try to find antiderivatives, but not every antiderivative even exists. Not only that, but you get a family of antiderivatives. You don't get just one function. You get a family of functions where they all have something in common. So going from function to antiderivative is a lot trickier than going from function to derivative. So going from capital F to little f is a lot more straightforward. That's why we start with that, than going from little f to capital F. So anyway, the integral represents two things. It represents an antiderivative, which is what we're looking at right now. And if you have no bounds, you have an indefinite integral with no bounds, then that means you are looking for a function and you have to take the antiderivative. And so that's the process you want to go through. And the antiderivative will always have a plus c on it, because if I were to take the derivative plus c, it would go away and disappear. So we don't know what that constant is. So that's one part of the integral is antiderivative. If we have bounds, that's called a definite integral. And if we have bounds, then we can find the area underneath the curve, or we can find the antiderivative and plug in the two values, the b and the a.